Bismillahirrahmanirrahim. Welcome to the third part of this topic, which is the divergence theorem. We say that the divergence theorem is a theorem that relates the flux to the triple integral or volume integration. Surface integral to volume integration, providing that the three-dimensional region space is closed and with smooth boundaries, or you can say surfaces. So the flux is equal to flux of a given vector function f that n equal to the triple integral over the given region D of the divergence of the vector function f, or the vector field. And we gave different examples before, and in this part also we are going to give more examples. So the first example here in that we see, we need to find or use the divergence theorem to find the outward flux f dot n, or the surface integral, given number one, f is equal to x squared to yz for z to power 3. This is our vector function. And D is the region bounded by the parallel pipe defined by x between 0, 1, y between 0, 2, and z between 0 and 3. So we need to find the flux, but using the divergence theorem, means using the triple integration. So flux, which is equal to f dot n ds is equal to the triple integral over d of the divergence. dB. This is equal to divergence of the vector function is equal to b sub x, the partial derivative of the first component, plus the partial derivative with respect to y of the second one, plus the partial derivative of the third component with respect to z. This is equal to now the partial derivative with respect to x, appreciate this with respect to x, I will have 2x. So it is 2x plus partial derivative of q with respect to y is 2z. And partial derivative of the third one with respect to z equal to 12z squared. And dv will be dx, dy, and dz. And the limits, since we start with x, we will with the limit of the x in the interior one from 0 to 1. This is x. Y, second one, from 0 to 2. And z is the last one, or the outer one, 0 to 3. Now we will evaluate this integration. So this is equal to 0 to 3, 0 to 2. We integrate with respect to x. This one will give me x squared. And we'll consider this as constant. With respect to x, it is constant. So this will be plus 2z plus 12 z squared x. And the limits from 0 to 1. This is with respect or for the x variable. This will give me 0, to 3, 0 to 2. Now substitute or replace x by 1 and then by 0. I will have 1 plus 2 z plus 12 z square. Now integrate with respect to y. And since we don't have any y variable in this integrand, so this is constant. All of this will be constant as function of y or with respect to y. So the integration is 0 to 3 of 1 plus 2z plus 12 z square multiplied by y. The integration is y because this is constant, there is no one dz, and y from 0 to 2. We have to evaluate the variable y from 0 to 2. That will give me 2. I will have 2 from this one. I will write it outside the integration as constant. So it is 2 multiplied by 0 to 3 of 1 plus 2z plus 12 z squared. Which is equal to 2 multiplied by z plus z square plus 4z to power 3 from 0 to 3. Evaluate with respect to these limits. I will have 2 multiplied by, replace it by 3, then by 0. 0 will cancel everything, but for 3 I will have a 3 plus 9 plus 4 multiplied by 27. Multiplied by 12 plus 108. And the final answer is 240. So the flux is equal to 240. Let's have another example. Number 2. With that, f is given by vector function, which is 15x square y, x square z, and y to power 4. And d is the region bounded by x plus y equal to 2, z equal to x plus y, and z equal to 3, x equal to 0, and y equal to 0. So let's find the flux for this vector function, and d is given by this region bounded by these planes. So by the divergence theorem, the flux or the double integration f dot n equal to the double integral of the divergence of the function f over the given region d, which is equal to divergence is b sub x plus u sub y plus r sub z dv, which is equal to v sub x. Differentiate this with respect to x will be 30 xy plus with respect to y, second one is given 0. There's no y in the second component. Third component with respect to z will be also 0. dv. I have 30 xy dv. dv is dz, because I have z as a function of x and y, so I will start with that one first. Then I use dy dx. We started with dz because what's given there in my boundaries, z is a function of x and y, so I have to start first with that one, x or z equal to x plus y. Now the limits for z are x plus y and z equal to 3. But also we have x plus y equal to 2. So we can see this is higher than this. The upper limit is 3 and the lower limit is x plus y. So the limit for z will be from x plus y to 3. These are the limit for the variable z. dy dx. Now let me leave this now. I will go back to this one later on. But now let's do it for the z. So the integration will be 30 x y z from x plus y to 3 dy dx. Which is equal to I'm going to go back to this one later on. So this will be 30 xy multiplied by 3 minus x plus y dy dx. Now we get rid of the z variable. All what I have is dy and dx. Now in the two-dimensional space, we have these functions, x equal to 0, y equal to 0, and x plus y equal to 2. This will be the remaining limits. Now x equal to 0 means y-axis. Y equal to 0 is the x-axis. And x plus y equal to 2 is this one. This is r. So this line is y equal to 2 minus x. And this one is y equal to 0. So the limit for y will be from 0 to 2 minus x. Now if y equal to 0, I will have 0 to 2 for x, the variable x. So these are the limits for dy and dx, or for y and x. Now integrate with respect to y, or I can open the bracket, then I will integrate with respect to y. This is equal to 0 to 2 minus x, 0 to 2 for x, it will be 90x y minus 30 x square y minus 30 xy square. dy dx. Yes, open the bracket. It's 30 multiplied by 3. I will get 90xy multiplied by x, which is minus x, where I get minus 30x square y. And with this one will be minus 30xy square, which is equal to 0 to 2. Now integrate with respect to y. I will have 45x y square minus 15 x square y square minus 10 x y to power 3 dx, and the limit between 0 and 2 minus x. Which is equal to, I can take y square as a common factor for these two, or I will leave it now. 0, 2 of, it will be 45 x multiplied by 2 minus x square minus 15 x square multiplied by 2 minus x all to power 2 minus 10 x multiplied by 2 minus x all to power 3 dx. This can be now simplified. I can take 2 minus x square as a common factor just to make it easier, then we'll multiply it. Let's take 2 minus x square as a common factor. I will have 45x minus 15x square minus 10x multiplied by 2 minus x. Which is equal to 0 to 2. This is 45x minus 15x square minus 20x plus 10x square. So 0 to 2, 2 minus x all to power 2. 45 minus 20 is 25x minus 5x square plus 10 is minus 5x square. Dx. I have now 4 minus 4x plus x square multiplied by 25x minus 5x to power 2 dx. We can open the bracket and integrate. So give me 0 to 2 of 4 times 25 will be 100x minus 20x square minus 100x square. This was this one plus 20x to power 3 plus 25x to power 3 minus 5x to power 4 dx. This will cancel. Oh, no, there's no cancellation for this one. Now I can integrate. I can combine these two, which is 45 x to power 3. Now integrate all of these. We'll have 50x square minus 20 over 3 x to power Also, these can be combined together. That will be minus 120 x to the power 2. So the integration will be 40. 40 x to the power 3 plus 45 divided by 4 x to the power 4 minus x to the power 5 from 0 to 2. Replace x by 2 because 0 will cancel everything. We will have this will be 200 minus 320 plus 160 for this one minus 32. So this will be 8. Yeah, the answer is equal to 8. So the flux for this vector function is equal to 8. So this is how to find the flux using the divergence theorem, just converting the double integral or just equate it to volume integration and evaluate the integration with respect to z, y, and x, and that's it.